Welcome, everyone, to 4 Ways to Put Your Model to Work with GENESYS, presented by David Long. My name is Donna, and I will be your host during today's webinar. For over 25 years, David Long has focused on helping organizations increase their systems engineering proficiency while simultaneously working to advance the state of the art. David is the founder and president of Vitech, where he leads the team in delivering innovative, industry-leading methods and software to help organizations engineer next-generation systems. He co-authored a primer for model-based systems engineering and frequently delivers keynotes and tutorials at industry events around the world. An INCOSE Fellow and expert systems engineering professional, David was the 2014-2015 president of INCOSE. Before David gets started, I have just a few housekeeping items. We will be answering questions at the end of the webinar. Please send your questions in as soon as you think of them through the Question tab on the webinar control panel. David will answer as many questions as he can today, but if we do not get to your question, we will reach out to you after the webinar. The webinar is being recorded. If you experience connection problems during the live presentation, a recording will be available within 1 business day. The recording will be published to Vitech's webinar archive located on our website. At the conclusion of this webinar, a survey will open on your screen. Please take a moment to give us feedback on today's presentation or on what topics you would like to see covered in future webinars. Now I'm going to turn the presentation over to David. Welcome, and thank you for joining us.
Thanks, Donna, and thanks everyone for taking time out of your schedule. As systems engineers, it seems like there's nothing we like to discuss more than model-based systems engineering. So we'll take the next 40 minutes to do just that. The interesting thing is, if you listen to the way we talk about model-based systems engineering, we tend to spend far more time talking about what it is, what does a systems model look like, how can I visualize it, how do I construct it. But if you think about other engineering models, we don't have those discussions at all. We actually talk about how do I put that model to use? How do I get value out of it? Now, this isn't overly surprising. Model-based systems engineering is still relatively new. The concept of a descriptive architectural model is a little different than the analytical engineering models that we're familiar with. But as we work to deliver value, it's critical to talk just as much, if not more, about how we use the model, not just how we construct the model. So with that, I need to deliver a little bit of context before we get into this. Context is always important as a systems engineer, and so let's begin with the context of systems engineering itself, because it helps differentiate what's special about these descriptive architectural models. So systems engineering often is framed as focused on complex problems, and that's not quite correct. The differentiator for systems engineering is that it's focused on transdisciplinary problems, problems that require more than one specialty to understand problem and or domain. And so in this world, the systems engineer needs to serve as the connective technical tissue of the team, helping to translate language, helping to translate insights, helping to translate concerns. And so we need to serve as a translator and a connector. That's critical for this descriptive architectural model that we seek to build. Because ultimately, what we're trying to do is to provide the whole team shared understanding of context, problem, and solution. And within that context, we are trying to enable their technical detail that provides the necessary insights to shape the design envelope and ultimately define the solution. Now, we have been seeking this shared understanding for the 50, 60 plus years of formal systems engineering practice, and the best mechanism that we had was the document. The document is not necessarily a great tool, but when you work across multiple specialists, and by the way, customers, users, and stakeholders, it was a knowledge representation that anyone could understand. What we're trying to do fundamentally is change that. Can we be better by going to a digital representation? And this is the so-called descriptive architectural model. Now, I always include that information in this chart simply to help define model-based systems engineering as I see it, as I use the terms, because it is such a muddy concept in industry. Fundamentally, I believe this is about moving from implicit to explicit communication. We're trying to make the descriptive architectural model, everything from first concept through behavior, through architecture and test, as well as the analytical models, explicit, coherent, consistent, and actionable. Actionable by humans, actionable by machines. And so we are evolving the mechanism by which we represent knowledge. Now, you've seen many different uses of that information here, but the key is, as we talk about changing from implicit to explicit, moving to higher fidelity representations, increasing the granularity of knowledge, you can start to understand why we spend so much time talking about what does MBSE look like, and also why we spend so much time talking about, well, is this harder than doing it the old way? Does it take more time? Is it more expensive? Personally, I will say that this is the way that I've always known how to do systems engineering. This is the way I was taught. It was the mental model that I was given. And so for me, it's not slower, it's faster. It's not more expensive, it's the only way I know to do it. But we should still focus on value. I've got a colleague at NCOSE who, I've anonymized, the guilty shall be protected, who likes to say, how many ergs of energy does it take for every diagram that you choose to draw when you're doing model-based systems engineering? It's typically a large number. And then he'll turn around and ask, and how many diagrams do you have to draw? Starting to give some scoping or scale of the investment to be made. And finally, if you're really following, he'll ask, how many ergs does it take to maintain what you draw? Because a system's design evolves as it is developed. And so we get a sense that being explicit for a given piece of data may require more effort. In total, we know that coherence and consistency of good information management pays for itself, but we still have to keep the investment and the return in mind. The value that we get from utilizing the model must exceed the investment made to construct and manage the model through life. One more contextual piece for those who may not be aware, I believe it was in 2018 that the Model-Based Engineering Manifesto was published. Note this is a model-based engineering, not model-based digital engineering manifesto, styled after the Agile Manifesto, but they felt it important enough to call out point 4, model usage over model creation. So often we complete model creation at the end of the program and we spend very little time utilizing that model to derive new value. So how do we change that? How do we make our model work for us? What I'm going to do is I'm going to walk through 4 different ways. I'm going to start out very basic. At the end, I'm not going to be advanced. I'll simply be a little more sophisticated. But I want to review those techniques on how we derive value from the model as opposed to what the model is and how we construct it. For each technique, I want to lay a little groundwork in PowerPoint so that we know what we're going to talk about. I will illustrate the concept using GENESYS, take you through how you would see it, how you would exploit it, and then come back to quickly summarize concept, cost, and value. It's going to be a little bit of a quick tour through these 4 ideas, but it should give you more tools in your toolkit for deriving value from the investment you make in model-based systems engineering, specifically the descriptive architectural piece of model-based systems engineering. At the very end, taking those 4 ideas in mind, those 4 ways to leverage models for greater value, I'll wrap up with a few key reminders because there's still some context and mindset that's important. So with that, let's start with the first one. And it's the one that is probably front of mind for most people. And that's the need and ability to visualize the model from many viewpoints. If you think about a classic document that is written to capture a system design or part of a system design, a given specialist has to read that document and construct their own mental model of what it means. One of the powers of model-based systems engineering is we should be able to take that common descriptive architectural model and look at it from a requirements perspective, a behavioral perspective that focuses on the actions, the activities, a behavioral perspective that focuses on information flows and item exchanges, a compositional or a structural perspective, a cross-cutting perspective on traceability. And so we have a transdisciplinary team. We need to be able to tailor the viewpoint to the audience and the analysis necessary at a given time. I'd like to illustrate this, well, with something I do every day. And so it is using a Cuisinart coffee maker set up with a little bit of water, a little bit of my favorite coffee, and the output is a nice cup of brewed coffee or a nice carafe of brewed coffee. Now, if you will give me a little bit of latitude, because all systems engineering should be fit for purpose, this is not going to be the most technically correct or technically detailed model of a coffee maker. It's not the purpose. The purpose is to illustrate visualization. What I've done, simply to save typing, is to create a number of functions. But what I want to do is quickly assemble them into a model and reflect the power of multiple visualizations during development and beyond. So if I look here in Genesis, I can see the views of this function called make coffee, and you'll see I have nothing right now composed. So I'm going to go ahead and create, I'll use an activity diagram to define the behavior of the make coffee, and I'll simply talk us through as we do it. I'm very familiar with it, so it's very comfortable for me. There are really 2 things that are going to go on in parallel here. There are the things that I will do as the user, and there are the things that the coffee maker will do as the system of interest. Now, if I start with myself, to set up the coffee maker, I need to do 2 different things. I need to add water. Oops, select here. Oops. So add the water, and then I need to add the beans. Doesn't matter which one of those I do first. Once both are complete, I can go ahead and turn on the machine, at which point control transitions over to the coffee maker. Now, the coffee maker can start its brewing cycle. I need to tell it that it's on, so I'll connect that via a trigger, call that the on signal. Okay, and then the coffee maker, I don't know the internals of the coffee maker, but I know a couple things about it that I can observe from the outside. It has to do 2 things before it can really begin. One of them is it must heat the water. And the other thing it must do is it must grind the beans. I use whole beans. When both of those are completed, it can process the hot water through the grounds. The result is I can then take my coffee. Okay, so I'm going to take a nice cup of brewed coffee back out. And sometime before I am all done, well, I should go ahead and clean the machine so it's ready for the next time, dump the grounds, etc. So there's a simple model construction. That's fine. But what if I want to visualize that in multiple different ways? Okay, that's good. How do we visualize things as processes, activities as a systems engineer? Oftentimes we'll look at decompositional hierarchies, a functional hierarchy. Whoops, need to do that with no selection here, so I'm doing it on my coffee maker. Let's reopen that. There we go. Not very exciting. I've only got one level of decomposition right now. That's fine. Well, one thing that we often use is we'll use a sequence diagram to focus on exchanges. This gives me the detailed process flow, but what are really the exchanges that are going on? I see here, I don't have a very exciting sequence diagram because I haven't done any allocation to the components yet. So let me come back. I could do it in either diagram. I'm going to do it here in the activity diagram, easiest for me. So I'm going to take the 5 things I put for the user and allocate them to the user. My sequence diagram started to get a little more exciting. I'll take these 4 things for the coffee maker, allocate them to the coffee maker. Okay, so now I've got a more meaningful sequence diagram. I can look up and see, yes, I've got the user and the coffee maker, their interactions. It's structurally correct. All the information is there. I can clean up the formatting a little bit. As I come down, as an engineer, I think, now hold on. At the end of the processing cycle, I often don't know if the machine is done. It feels like it's done before it actually finishes dripping. So you know what? I would like some sort of signal that tells me that this is completed. So I can come right here, different insight, different visualization. So I'm going to add a completed signal. So not only do I pick that information up here on my sequence diagram, but as that colleague said, how many ergs of energy does it take to maintain? Well, the answer is hopefully the tool is doing that for you, keeping everything in sync. Now I'm going to use one more visualization here because there's a classic visualization that has information that's not present on any view that I've seen yet. And that's the EFFBD, the Enhanced Function Flow Block Diagram. Looks very much like an activity diagram turned on its side, but there is not only different notation, but there's some different information content possible. I'm first going to shift this over a little bit just to get a better layout. Again, you know, substance with style. But in reality, there's a reason that I add water, and there's a reason that I add beans. I'm adding resources that the coffee maker needs to use. So let's go ahead and add the water up here. Okay. Move him out so he's a little more visible. This will produce the beans. And then I can connect those flows up as well. My coffee beans will be used in the grind step, be consumed actually in the grind step. The water, even though it's heated in heat water, it's not actually consumed until the drip hot water. So I'll connect down there. And now that one, if I go back, whoops, close that out. If I go back to my diagram here, I don't see a change because resources aren't represented. That's fine. So what we've seen very quickly is one of the values of model-based systems engineering is that you can look at the model from different perspectives. Perspectives that are tailored for a particular insight. Am I talking about process? Am I talking about exchange? We didn't look at requirements. But also visualizations that are formatted for different communities, different users. One more of those, okay, and it's one of the notable benefits out of putting your model to work. You should be getting your specification, all of your documents directly out of the model. So rather than stopping the engineering process to go engineer a document, the document should be just one more view, one more visualization. And it's perhaps in early adoption of MBSE, it's one of the highest return on investments because if you notice a flaw in your document, you simply go back, you correct your system model, you republish the document. No additional investment. So if we now look, so what we're talking about here is visualizing the model from many viewpoints, diagrams, tables, specifications, all of them are views. All of them should be projections of the model. All of them should help bring new insight or help you connect the transdisciplinary team. The net cost of this to you, it really should be zero. This should be something that your model-based systems engineering environment is providing for you. And the value, certainly the return on investment, if the investment is low, the value is very, very high because it's increased effective engagement of the team. So you've got better progress towards a shared mental model of problem and solution. And you have the insights born of multiple perspectives. Different visualizations help you see different things. This is the most basic way to use the model, so I wanted to begin here. What's the next step? Well, the next step is, can we use that model to assess completeness and integrity? Now, this requires that there are underlying semantics to your model. These checkers need to mature as the project matures. On day one of the project, I don't expect that my requirements are mapped to the solution. I don't expect that I've got verification in place. But as I progress into day 180 and year 3, I want to run more detailed completeness checks and integrity checks. Now, there are two types of checks here listed. One is completeness. This is the one that we generally think of. It's classic systems engineering bookkeeping. Do all my entities have descriptions? We're really bad about just putting boxes on diagrams and thinking that we've modeled. That's not true. That's a very ambiguous form. We need to be more explicit. The questions, the issues, the concerns that have been raised, when they've been closed, did I document a decision? Did I document a rationale? Are all the requirements satisfied? Are all the leaf level functions allocated? Do I have anything unaccounted for? Classic bookkeeping, but we can go beyond that to reasoning. And these are the design integrity type checks. So if I've got a model with design parameters, design dependent variables, if you wish, and I say that my objective value for my mass is 10 kilograms, is the mass of the system below or equal to 10 kilograms? If not, is it at least below a threshold, not necessarily the objective value, but the threshold value? Does my design satisfy the constraints? As we move through layers of aggregation and decomposition, have I done the bookkeeping correctly? Have I accounted for all of my inputs and outputs, or have I lost anything? There are rules about what is valid decomposition. MBSE should help you follow that. And then the slightly more sophisticated one is, do links exist to transfer items between functions? So if you have function 1 allocated to component A, function 2 allocated to component B, and those functions exchange information or an item, then you know there must be some connector, some link between those components. Can I use MBSE to confirm that bookkeeping for me? The answer is absolutely yes. So if I come back now to my model, I can look over at the diagnostics. In GENESYS, the diagnostics are always present, simply a new tab. And I can see I was very quick and casual in my engineering. I just created a function. I didn't provide a description to it. Easy enough. I can correct that. Just to show you the effect live, I will open a property sheet here, and I will give it a description. Provide brewed coffee from supplies. The moment I enter that, my completeness check passes. Okay, not overly compelling. Let's look at the more interesting item that I noted at the end, the exchange of items between components. So if I navigate now to, let's look at that completed signal, the way that the coffee maker tells me it's safe to remove the carafe. So it has two errors. The description has not been specified. Okay, we saw how to fix that. But here's the more interesting design integrity error. Leaf level items that flow between functions that are mapped to different components have to be transferred by a link that connects the components. Makes absolute sense, but it's a classic engineering error that occurs at the interface. We don't account for the exchange. So let's go ahead and correct that. Now, the completeness checkers and integrity checkers won't solve this for you, but they're a good computer check behind the scenes to help bring everything into sync, to bring those errors to the surface so you can solve them. So I need to make that transferred by, let's say that I just want a visual indicator. So I'm going to use the visual spectrum as my connective link. Okay. Now, in Genesys, the completeness checkers run every time you change a field. They're very, very quick. Design integrity checkers can be more sophisticated, so they change when you tab off and tab onto the sheet. If I click over to on signal and back to completed signal, I may have mapped my item to the link, but that link is free floating. So I actually haven't solved the problem yet. I actually need to go in and I'll take this link, bring it up in a property sheet, and I'm going to have it connect the two sides. On one side, it's the coffee maker sending the message. On the other side, it's the user seeing it. Okay. So now my link is wired up. My item is being transferred by that link. And if I click off and click back on, I've resolved the problem. Now, those are just two examples. If I were to show you a more exhaustive list in Genesys, let's see here. If I search on completeness, so I can look at the completeness checker in the help file, and I can see the very specific rules, and you'll start to see the kinds of rules that we've defined based on our semantics. These are tailorable by you, and you should tailor them to fit your specific domain and your specific process. Okay, so these are completeness rules. You see that we've defined them by class, by different levels of abstraction. If I come in and look at the design integrity checker, these are rules that look across sets of data. And so if I look here, I'm going to see different ones, you know, connectivity between components and links and how things must be mapped into children's. We see a lot around the functional area that has to do with rules of decomposition for validity, so on and so forth. There is, by the way, one more way to visualize these or to see these completeness errors. You don't have to look at them one at a time. You can certainly run a report. Here's a report I ran earlier just for convenience. It's on a different model, but just gives you a flavor. We can all think about requirements, and we can think about, well, my requirement needs to be connected to something. Here I've got a requirement that's just completely free-floating in the model. I was good. I provided a description for everything. The parameter types are good. The origin is set. The type is set. I've not been good here about mapping these into my solution, and I've got 4 that are not verified. I don't have any design integrity errors. I just have a lot of completeness errors. So the second way we can make our model work for us is let computers do what they're really, really good at, which is bookkeeping. Systems engineering is a combination of bookkeeping to make sure that you account for all the parameters, all the relationships, all the mappings that you need to do, and creativity, inspiration. Let the computer do the bookkeeping so that the engineering team can spend their time on creativity and inspiration. The cost, it should be low to zero. Again, this should be reasoning that is included in your model-based systems engineering environment with tailorable rules that allow you to adjust based upon your process, your methodology, your application domain. The value, it's very, very high. particularly because the investment is so low. If we free the engineer, that frees them for going deeper, going broader, exploring other alternatives, while they can do so with the confidence that they will not overlook something. All right. Item 3. Not going to go as deep in item 3 or item 4 because we have just separate webinars on these, and I will point you to them later. But here it's simulation. So can we prove that the behavior that we developed actually works? It's very, very easy to draw a diagram. But when you think about it and when you reason it, those diagrams don't work. And so if this is actually defining the design envelope, if this is specifying design, and we've got a system level design that won't work, and then we partition it out and give it to the component level design teams, we've just set them and us up for failure. So from day one, I sure would like to be able to dynamically validate that behavior. Make sure that it can at least work. Okay, let's do that. We're going to start again in the coffee maker that we were working with. And so here's that coffee maker. I will go ahead and open the simulator beside it. Okay. Now you'll notice I haven't done anything special here. When I put a block on the diagram, there's just enough semantic meaning that GENESYS can process it. So let me just get this laid out so we can see enough. And I'm going to step through simulation. Now, at the first level of dynamic verification, we're really just looking to see, does this work? When I have forking paths, I can often create deadlocks where something upstream is dependent upon an item that isn't generated until later. And so we can have processes deadlock against each other. I'm going to step through at this first level and just make sure that it all works. And the answer is, this was a very simple model. Yes, it does work. I could go to the next level and I could begin to do timeline analysis. And if for market reasons, it's critical that I have that fresh brewed carafe of coffee within 5 minutes, I could begin to allocate time budgets against each of these steps and make sure that from me hitting the on switch to me retrieving the cup of coffee, it does it in 5 minutes. Let's go to a slightly more sophisticated model to see some of this. I'm going to close that out. I'm going to come back and I'm going to open a different model that I've got. It's a fast food model. It'll show you a little more richness as it comes up here. Okay. So in this fast food model, I'm going to go into the EFFBD, the Enhanced Function Flow Block Diagram, because resources play an important role in this particular model. So think of your favorite fast food restaurant. At least think of it while we were not in shelter-in-place type rules. And so what we have up top is we have some arrival function for the customers. How quickly are they arriving? We've got a service area where the order is taken and they assemble food. Then the customer can take the food, leave the line, eat in, carry out. And at the bottom, we've got a function to cook the burgers. Now, I can do the same thing here. I'll open the simulator. I'll go ahead and get it running. Okay, we'll see things flash through on the model. And we could begin to see, where do I have waiting occurring in my model? So we're seeing the resources, how many burgers are available to fill orders, how many customers have come in. We could follow a specific customer through. For those who are familiar with the GENESYS simulator, you know that yellow reflects where a function is ready, but it can't execute because it's not been triggered. Rose, which is when this finishes here, we'll see it. There we go, just finishing now. There's a little bit of rows right up here on the front where I couldn't execute because there are no burgers available. so I've got a customer waiting. Now imagine your normal fast food restaurant, say 2 o'clock in the afternoon, it's not overly busy. Think of it closer to maybe 11:30 or 12 when the lunch rush hits. I should be able to put this model to use and begin to game different scenarios and understand. So if I come back in, I'm going to look at my customer arrival, and it was currently set up for they arrive on a normal distribution, mean of 5, standard deviation of 1. Well, that's interesting, but I'm going to change this up for the lunch hour. I'm not going to have any more people come through. I'm going to have them arrive much quicker. So standard deviation of 1, sorry, a mean of 1, standard deviation of 1/2. Okay, close this. I'm going to reset and run again. Now, the interesting thing about systems is they're complex. We don't have a linear relationship between cause and effect. Oftentimes, when you look at a system design, you would look at it and say, if this is running too slow, maybe I should accelerate the cook burgers function. Can I figure out a way to make that take 20% less time? Well, what you find is sometimes changes that you think will help have no significant impact because of the nonlinear interactions that go on with your system. So your only choice is probe, sense, respond. And using dynamic validation allows you to rapidly probe, sense, and respond. Here I've got a long wait that's occurring because I'm out of burgers. And so I could try different scenarios. What if I added a second cooktop to my restaurant if I had the space? Is there a way I could cook things faster? Well, it turns out one of the earliest systems engineering lessons I learned came from my father, and it is why secret sauce exists at fast food restaurants. And the answer is simple. A fast food burger hot tastes just as good as a premium burger. However, they can't cook quickly enough to stay up with demand during peak times. The only way to cover up that taste is secret sauce. So the solution to this problem for a fast food restaurant is they actually have to have a backlog of burgers ready before the lunch rush. And then you get secret sauce to cover up the taste. I hope I didn't ruin anybody's lunch or ruin any industry secrets there with that one. Okay, so what we've got here is in dynamically validating behavior, there are 4 different things that we can look for, really. And there is a increasing cost for each of these. The first is just dynamic analysis, looking for those deadlocks. Again, that should fundamentally be free as part of your tool. The next step is timeline analysis. If I need to get the burger, the customer, from order to burger in hand by 90 seconds, if I allocate my timeout, can it happen? That requires more investment on your part, but it delivers more value. Then you layer in resource analysis if it's important. And at the very end, flow analysis. We saw earlier that items have to flow across links. Those links can become congested, just like cars on the highway. And so flow begins to delay exchanges. This is a case where you need to decide how much you value, because each step further that you take does require more investment on your part. But if it's necessary, there is return on that investment. It's just a diminishing return. Higher investment, lower return. All right, last way, and this is integrating architecture with analysis. Everything that I've talked about so far has actually been the descriptive architectural model. But there are really 2 models at play in MBSE. There's the descriptive architectural model that reflects how we move from first concept of need through delivered system. And then there are the analytical models, the ones that we have grown up with in engineering that bring the rigor to this. What I'm going to demonstrate is the simplest possible example. and that's going to be a separate model in MATLAB, but there are many different ways to do this. We have a separate webinar that talks about MATLAB, from 2017. There's a 2019 webinar that talks about a more sophisticated integration of using GENESYS with Phoenix Integration's Model Center to integrate these specialty analytical models around the outside so you can do multi-domain analysis and optimization. Once you understand the concept from one, you can extend it to all. So let's go back to GENESYS one more time. Okay, and I'm going to open one more different model. This one's a model that's specialized just to focus on these analytics. Now, one of the nice things that SysML brought us in SysML v1 was the concept of parametrics. And parametrics give us the ability to represent the relationships between design-dependent and design-independent variables in our solution space. Fundamentally, think of these as the physics that govern the solution. And so here we're looking at an engine torque model that is for a vehicle. If I take a simpler piece of this, because parametrics can get complex quickly, and look at it as a parametric diagram, what the parametric diagram allows me to express are the relationships between different functions, different parameters. So force basic motion, F equals ma. Well, we've got these variables that flow. We've got variables down from a different constraint, a different equation, if you will. We've got variables that are a function of the vehicle, the weight, the number of passengers, the luggage, etc. So parametrics give us a way to bind all of these values together and then actually compute from it. And so in this case, we will simply, for example only, use the MATLAB constraint solver, which will actually solve the constraints in the model and any dependent constraints. I'm going to take the total required driving force. And what happens here is traversing those parametric models, getting to the design parameters, it's pulling out the various values in the descriptive model, and then we've got the expressions, the physics, so to speak, and it's converted those into a MATLAB script that can be solved by MATLAB. I will go ahead and do so. The same concept can be applied many other ways. In the example of Model Center, what is transitioned to Model Center is the bindings that would connect together higher fidelity external models. It's solving the script through MATLAB. Oops. Let's see here. Where did my screen go? I've got too many screens open. Here we go. It came back with the values. I can go ahead and update those in my model, and it tells me these values were updated, these were unchanged. Simply use this as an existence proof. One example. The key concept here is the same way that the systems engineer is the technical connective tissue for the engineering team, the descriptive model is the connective tissue for the engineering analytical models. Wherever they reside, you can connect them. Now, the cost here is actually the highest. And the reason that the cost is the highest is as you work between these various engineering domains, you must map the semantics. Different domains use different words to mean the same concept. And you have to get those mappings correct. So there's intellectual exercise to do that. This means that you need to manage your investment. Keep it to the systems level. The classic error I see here is people go too deep, too fast. Don't cross into the detailed design space. Stay at the system level. We're trying to define validity and the design envelope. If you work at the system level, it's high. It's even higher if you look not only at the technical figures of merit, but put a similar parametric model in place for the business value function. There is a value function that drives how valuable your system will be. If you have both of those and you can execute them in parallel, you can see how changing aspects of the design affect simultaneously technical performance and business value. The value of integrating architecture with analysis rapidly declines as you move into detail, because that's just not the space you should be living in. So 4 different ways that we can make our models work for us. The most basic, visualizing from multiple perspectives, multiple viewpoints, to help the team leverage the power of multiple perspectives, transdisciplinary insights. Second, bookkeeping, assess the completeness and the design integrity, freeing the engineer to be creative, inspirational. Third, dynamic validation of that behavior. It's simply very easy to design a time machine. It's much harder to actually build one. And so this is a way to validate your design on the front end. And fourth, connecting the engineering rigor with the descriptive architecture. Now, a little guidance on how you make the most of your investment. Systems modeling does not equal systems engineering. That fact seems to be lost on many today. Many people are just prioritizing systems modeling over everything else, thinking that, well, since we're doing model-based systems engineering, it must be all about the model. That's not true. Our purpose is engineering, or more specifically, delivering value via the system of interest. Our purpose is not modeling. What we need to do is spend our emphasis in the overlapping piece of that Venn diagram, and then make sure that we tend to the other aspects of systems engineering. How do you do that? Well, on day one, you need to define the questions that you're seeking to answer. All models are approximation. As Box says, all models are wrong, some models are useful. The remainder of that quote is, the question is, how wrong can the model be and still be useful? You define that when you state what questions you're trying to answer. If you don't know what you're trying to answer, you're going to do too much modeling, too much investment, not enough return. Once you know what you're trying to do, tailor the approach to the problem and the context, where the context is the combination of your process, your methodology, and your supporting tool. Take advantage of what your tool has to offer if it helps answer the questions you're seeking to answer. Good systems engineering, good model-based systems engineering is always fit for purpose. And my final comment, engineering the system is our objective. Systems engineering is our vehicle to do it. Systems modeling is a tool in that portfolio, not the purpose. Begin with the end in mind. We are trying to deliver value in the most effective and efficient manner. We do so by using system modeling as a tool, maximizing that overlap, but making sure that it is all fit for purpose to answer the critical questions that enable us to engineer the system and ultimately deliver value. Thank you. And with that, we'll turn to questions in the remaining 10 minutes.
Thank you, David. We do have a few questions, thanks to all our participants. I encourage you to join the discussion now and submit your questions using your webinar control panel. If you do need to leave the webinar, please take a moment before you go to respond to the quick survey that will pop up on your screen. Our first question comes from Luke. It says, how can we integrate MBSE to engineering tools, ECAD, MCAD, etc., defining the solution and make sure the solution matches MBSE definition?
So, Luke, that's a critical question in how we further leverage the descriptive model. And I did not cover it here, But what we have found most commonly is the connective point between systems engineering and the detailed design domain, regardless of which domain we're talking about, is at the systems level, it's the system schematic. You could consider it the internal block diagram. You could consider it the physical block diagram. But effectively, what transitions from system to detailed design is that system schematic that shows the parts and their interconnections. And the reason that that's the transition point is from those parts, you can query back into the MBSE source of truth and see the allocated functions, the allocated requirements, the design parameters. So what we have found every time that we have done this integration is past that IBD, past the internal block diagram for a particular component or subsystem down. That becomes the lowest level representation at the system level, the highest level at the detailed design level, and then use queries between to get the rest of the specification. If you think about it, you just passed the digital specification from system to detailed design.
Okay, so our next question comes from Mike. How much analytical modeling should I do at the MBSE descriptive architecture level, and how much should I do later?
So this is where I noted that the most common error is doing too much. Well, actually, let me modify that. It's kind of a bimodal distribution. Some people do no analytical modeling. That's wrong. Some people do way too much. That's diminishing returns. The question that I ask is, actually on day one of the program, what are the fundamental physics that govern the performance and the value of your system? There are a few equations. Now, I say physics there as a shorthand. It's really any equation. So what is the minimum subset of equations that you could state that help describe system performance and system value? Start there. Every time you go beyond that, question, is this a system level concern or is this a detail concern? One of the things that I observe is that we are losing accuracy in the pursuit of precision. Now, how can that be? Well, it happens because when you pursue precision, you get so detailed that you often miss the big picture. I see people debating the microbe on the bark. They don't know there's a tree, and they certainly don't know there's a forest. The way you remember the forest is to find just a couple of governing equations, performance and value at the system level, and question yourself every time you try to go beyond those.
Okay. So our next question comes from Lisa. I haven't seen the highlighting in the simulation before. Is that new?
You caught me, Lisa. So the answer is yes. That's a capability that we had in Core long ago, but we had not had in GENESYS. That capability is now in the latest release of GENESYS, GENESYS 2020, which will actually go live on our website today. It actually takes the old Core capability to a new level. And as you're stepping through a simulation, it lets you know not only the functions that are currently executing, but functions that are enabled, but they haven't been triggered yet, are shown with a yellow glow to match the yellow in the simulation. Those that are enabled, but the required resources aren't available, are shown with a rose color, again, to map to the simulator. And it's just a tool that helps you step through and follow what's going on. It's a visualization tool that helps with understanding.
Okay. We have one final question from Brian, and this is about the completeness and integrity checks. Can these be customized for my purpose?
Yes. So the ones that I showed are based on the standard Vitek methodology and approach. They are in the GENESYS solution, they're handled by scripts. Those scripts are very easily extensible. We recommend that you tailor those to reflect your methodology. So, you know, how do you handle a particular concept in systems engineering? What do you want flagged? And certainly, anytime you extend the structure of the schema to indicate your specific concepts, anytime you extend the schema, you should also question how you extend the completeness and integrity checks to reason about that new concept that you added.
Okay. Well, thanks, David. That wraps up the final Q&A for today's presentation. If you have any other questions or comments for David, don't hesitate to send him an email. You can see his email address on your screen now, or you can post your questions and comments on our LinkedIn group page. Just visit linkedin.com and search for Vitek Corporation. Thank you so much for attending today's webinar. We want to let you know about a couple upcoming webinars. David will be presenting Solving the Systems Engineering, Digital Engineering, and MBSE Puzzle on May 13th at 2 p.m. Eastern. And Zane Scott will present There is No Such Thing as Non-Model-Based Systems Engineering on May 21st at 11 a.m. Eastern. Please sign up for these through our website. Remember that at the conclusion of this webinar, a survey will open on your screen. Please take a moment to give us feedback on today's presentation or on what topics you would like to see covered in future webinars. Once again, thank you for joining us and have a wonderful day.